Let's work through exercise 21 from chapter 7. A 120 gram arrow is shot vertically from a bow. So let's write down the mass there, 120 grams. Convert it to kilograms. A bow whose effective spring constant is 430 newtons per meter. If the bow is drawn 71 centimeters before shooting, so let's say x is 71 centimeters or 0.71 meters, to what height does the arrow rise? Okay, so we're trying to find the height when the final velocity, let's call it v2, is equal to 0. Okay, so I know that this is chapter 7 and this must be a conservation of energy problem. But let's, just for fun, try to use forces. Will the forces method work here? Well, we have to start by drawing a free body diagram for the arrow while it's on the bow. So the bow is stretched downwards. We can call the equilibrium of the bow y equilibrium. It's stretched down a distance x, so the x is equal to y equilibrium minus y, where y is the height off the ground. So the force of the spring, kx, upwards, will be k times y equilibrium minus y. So there's the free body diagram. There's a spring force up. There's the mg down. So the net force, which is m times a sub y, in the y direction is k, y minus y minus mg. We can solve that for a sub y, which is d squared y by dt squared. It's negative k over my plus these other constants. So can we solve this? Well, yeah, we can. This is called what's called a second order linear homogeneous differential equation with constant coefficients. That's actually not as hard as it sounds to solve. Its cosine is the solution. We will get to that later in the course, but basically this is not the easiest way to solve this problem. You can do it, but better to just use conservation of energy. We're in chapter 7, so let's do it. Let's set up before and after. We'll call before when the arrow is pulled all the way down just before it is released up into the air. So we can draw that out. There's the little arrow. Its initial speed is actually 0 when just before you release it. We know that it's stretched down 0.71 meters. We can define that to be the bottom, y1 equals 0. So E1, which is the initial mechanical energy of the arrow, is the kinetic energy plus the potential energy. So kinetic is 1/2 mv1 squared. Potential has two parts, mgy and 1/2 kx squared for the gravitational and elastic. So v1 is 0 and y1 is 0. So those two parts of the energy are 0, and so the initial total mechanical energy is just 1/2 kx1 squared. So that's the initial. Let's look at the final energy now. So at the top of the path is where we're trying to find the arrow. So we can see it going up to the top of its path. V2 equals 0. That defines the top of the path. Y2 would be the height that it reaches. This is what we're trying to find. And if you think about the bow is released, meaning that there's no more elastic potential energy in the bow. So we say there that x2 equals 0, meaning that the bow is now at its equilibrium position. Okay, so we can write down now E2, the final energy. This is going to be the sum of K2 plus U2, the final kinetic and potential. So 1/2 mv2 squared plus mgy2 plus 1/2 kx2 squared. So V2, final speed is 0. Also x2 is 0, as we discussed. So final energy is just mg times y2. Okay, so now we just apply conservation of mechanical energy, and we're assuming here that there's no loss due to air resistance. So E1 equals E2. That's our equation. We got those at 1/2 kx1 squared equals mg y2, and now we just solve for y2. So it's pretty simple. Just rearrange. Y2 is kx1 squared over 2mg. We can plug in all the numbers we have in SI units, of course. Plugging that all into my calculator, I got 92.16, so that rounds to 92 meters. And just remember that this is above the arrow's lowest point when it was stretched. So there's an extra 71 centimeters there. If you wanted, I guess you could subtract the 71 centimeters if you wanted to find the position above the arrow's equilibrium position. And that's it.